Today we are going to go over 5.1, the natural log function, differentiation. How do we take the derivative of Ln function? So the definition of natural logarithm function is given here, Ln of x. So this is what we call the natural log function, and base is e. And on the right side is a graph of Ln of x. The log function goes through 1, 0 when x equals 1, y equals 0, and it's increasing as x increases. When x approaches 0 from the right, 0 plus the limit approaches 0 from the right, limit is negative infinity. When x approaches infinity, the limit equals positive infinity. And also some properties for logarithm function. So if you look at Ln1, give us 0. So for any other base, it's the same property. Log any base of 1, give us 0. Ln a times b equals Ln a plus Ln b. Ln a to the power of n, the power n can be moved out, so it's n times Ln a. Ln a over b give us Ln a minus Ln b. Okay, everybody, you can pause the video for 2 minutes and you can finish example 1. After you finished, you can compare your answers with mine. Check all the details, part A to part E. The next will be the derivative of the logarithm function. As we learned before, when we take the derivative of Ln of x, give us 1 over x. And by definition, this x instead of Ln has to be positive. And other than x, if the inside is a function of x, we have to use the chain rule. 1 over u prime here. I'm going to finish example 3. You can pause the video and solve it yourself in 2 minutes and then compare your answers with mine. After you finish example 3, you can compare with my answers. Example 3 is the direct application of the derivative. And example 4 give us some examples. How do we combine the properties and find the derivative? Okay, you can pause the video now for 2 or 3 minutes and then check your answers. After you finish example 4, you can compare your answer with mine. Just if you look at part A and part B, I use a property to simplify the function first. And then I take the derivative. You can leave your answer like this as an FRQ question, but you also need to be able to simplify it if it's given as a multiple choice. And for part B, it's a little bit more complicated, but it's the same steps. The property, division becomes subtraction, and then take the derivative. Sometimes it's useful to use logarithm to help you to find the derivative of any complicated function, especially as a fraction with complex parts. Given y equals a fraction, and if you look at the fraction, we have the power and we have square root. So we are going to introduce Ln on both sides. So Ln y equals Ln x minus 2 squared over square root of x squared plus 1. Next, we are going to use a property to simplify the right side. Give us 2 Ln x minus 2 minus 1 half Ln x squared plus 1. Next, we are going to take the derivative, chain rule on the left. On the right will be 2 over x minus 2 minus 1 half times 1 over x squared plus 1 times 2x. We simplify a little bit. Minus x over x squared plus 1. So now we can multiply y on both sides. So y prime equals y times 2 over x minus 2 minus x over x squared plus 1. Now you can just replace y. Just plug in y. So on the test, if y is very complicated, you can leave your answer like this. Number 6, we are going to use the derivative to find the equation of the tangent line. And when we take the derivative, we have logarithm function here. but the steps are the same. So first we find the slope, we find the derivative, which is 6x minus 1 over x. So the slope will be the derivative at x equals 1. So we plug 1 in, so 6 minus 1 give us 5. After we find the slope, we just use the point slope formula. 5 times x minus 1. That's the equation of the tangent line. Example 7 is how do we find relative extrema given any function, and in the function we see logarithm here. So same step, we just take the derivative. So y prime equals 1 over x squared plus 2x plus 3. Don't forget chain rule, 2x plus 2. Now we simplify a little bit, so it's x plus the denominator. We cannot do anything. The numerator plus 1. So now we take the derivative, set the derivative equals 0, find a critical point. So that means x equals negative 1 is our critical point. So first step, second. Next, we are going to do the sign analysis. Negative 1. On the left side, if you look at the denominator is always going to be positive. So when x, you plug negative 2 in, for example, will give us negative. And when we plug 0 in, give us positive. So the derivative changes sign from negative to positive. That will give us relative minimum at x equals negative 1. Y equals, we plug negative 1 in into the original function. So it's Ln 1 minus 2 plus 3 give us Ln 2. That's our relative minimum value. So let's have a look at example 8. How do we show the function is a solution to the differential equation? So if you still remember, differential equation are the equations have the derivative. It doesn't matter first derivative or second derivative, as long as you have a derivative, which we call the differential equation. And given differential equation, how do you check if a solution y, if y is a solution or not? We just need to plug in y. So given y prime equals 2 over x, and y double prime, we take the second derivative, which is 2x to negative 1. So it's negative 2 times x to the negative 2. Now we can plug y prime and y double prime into the equation. So x times negative 2, x to negative 2, plus 2 times x to negative 1. Let's have a look. So it's negative 2 times x to negative 1 plus 2 times x equals x to the negative 1. Give us 0. So 0, the left side equals 0, the right side equals 0. So proved. As long as the y satisfy this equation, we call y equals 2 times Ln x plus 3 is a solution to the differential equation.